Everything you've been told about how stars die is a guess. For a century, we've looked at the corpses of stars, glowing clouds of gas like the Crab Nebula, and tried to work backward to the crime scene. We had the math, we had the simulations, but we lacked the one thing that matters, the first 10 seconds. On April 11, 2024, the clock finally hit zero. 22 million light-years away in the galaxy NGC 3621, a star 15 times the mass of our Sun just snapped. This is SN 2024 GGI. For the first time in human history, we didn't just find the aftermath, we caught the explosion as it was breaking through the surface. And what we saw? It shouldn't be possible. It's a shape that breaks our best models and points to a hidden engine inside the universe's most violent fireworks. Today, we go inside the breakout. Imagine being Yi-Yang. You've just touched down in San Francisco, your head is spinning from jet lag, and all you want is a bed. But the universe doesn't care about your sleep schedule. His phone began to explode with alerts from the Atlas survey. Atlas is our early warning system, 4 telescopes spread across the globe that act as the tripwires of the cosmos. They had spotted a transient, a sudden spike in brightness. But this wasn't a slow burn, this was the breakout phase. In the world of astronomy, finding a supernova is common, but finding one in its breakout phase is like catching a lightning bolt in a bottle. Most supernovae are found weeks after the fact, when the original evidence has been incinerated. But 2024 GGI was found in hours. The stakes couldn't have been higher. Yang knew that if they didn't act immediately, the data would become scrambled eggs. As the explosion expands, it hits the gas and dust surrounding the star, masking the true shape of the blast. To see the heart of the explosion, they needed the most powerful eyes on Earth, the Very Large Telescope, or VLT, in Chile. They had to beg for director's discretionary time, an emergency request that bypasses months of waiting lists. They were racing against a clock that was ticking at 10% the speed of light. When the data finally came back from Chile, the atmosphere in the room changed. Astronomers have always assumed that when a massive star goes boom, it does so relatively evenly, a sphere expanding into the void. But the light from SN 2024 GGI told a different story. The supernova wasn't a sphere, it was an olive. In technical terms, it was a prolate ellipsoid. To find this, they used a technique called spectropolarimetry. Think of it like a pair of cosmic polarized sunglasses. Light waves normally vibrate in every direction, but when light reflects off an asymmetrical surface, it becomes polarized. It vibrates in a specific direction. If the supernova were a perfect circle, the polarization would cancel out to zero. But Yang saw a strong, clear signal. The light was being scattered by an explosion that was bulging at the poles. The star wasn't just exploding, it was being squeezed. To understand how a star turns into a football, we have to look at the iron dead end. A star is a factory that turns hydrogen into heavier elements, releasing energy that holds gravity at bay. But once the core hits iron, the factory goes bankrupt. Fusing iron consumes energy instead of producing it. The outward pressure vanishes, and gravity, which has been waiting for millions of years, finally wins. The core collapses inward at 23% the speed of light. This collapse is so violent that it reaches the nuclear equation of state, a point where matter becomes so stiff that it cannot be compressed further. The core becomes a proto-neutron star, and the infalling layers of the star slam into this solid wall. They bounce. This is the core bounce. But here is the mystery. Our best computer models show that this bounce isn't enough. The shock wave gets tired as it pushes through the star's outer layers and stalls. In theory, every star should fail to explode and simply become a black hole. Yet we're here, and the universe is full of heavy elements. Something revives the shock. This leads to the great war of astrophysics. On one side, you have the neutrino theory. This standard model suggests that a flood of nearly massless neutrinos heats the gas above the core, causing it to boil and push the shockwave back out. But there's a problem. When we simulate this in 3D, the explosion is messy, lopsided, and wobbly. It doesn't produce the clean football shape Yang saw. On the other side, you have the jet theory. This suggests that if the star is spinning fast enough, its magnetic fields wind up like a rubber band, launching two powerful jets out of the poles. This creates the perfect olive shape. But jets are notoriously unstable in simulations. If the star has even a tiny wobble, the jets fail. The solution might be the jittering jet theory. Instead of two clean, stable beams, imagine a chaotic engine where the jets wobble like a loose garden hose. This chaos actually makes the explosion more robust, depositing energy in a wide cocoon that drives the star apart while maintaining that overall axial symmetry. We are now entering the big data era of space. Tools like the Vera Rubin Observatory and NASA's SphereX are about to change everything. We're moving from a world where we find one breakout a year to a world where we find 1,000 a night. This matters because you are made of this chaos. Every atom of iron in your blood and every bit of calcium in your bones was forged in the heart of an olive-shaped explosion millions of years ago. We aren't just looking at a distant star, we're looking at our own origin story, caught in the act for the very first time.